Today I'm happy to share 5 ways that I see nature effectively producing heat transfer that I think you can copy or mimic in your cooling designs. Let's jump right in. Have you ever noticed that your ears and toes and fingers are the parts of your body that feel the coldest in winter? And you might not have ever stopped to ask yourself why, but it's because they have a high surface area and are dissipating more heat because of it. For any temperature difference between hot and cold reservoirs, heat transfer is directly proportional to surface area available. And that's why you see fins and pins on many of today's electronics and heat transfer devices. Moving beyond adding surface area, you might be familiar with the effect of sitting in front of a fan on a hot day. It cools you off, right? With fluid movement, a form of heat transfer known as forced convection is enabled. Without forced fluid movement, heat can be trapped in a stagnant fluid layer that effectively insulates the body that you're trying to cool. While heat transfer depends on fluid velocity and application specifics, forced convection can generally produce about 10 times or more heat transfer than natural convection alone. A classic example is the flow of air over your automobile's radiator grill as you move along the highway. An example of that is shown here on the left. Another feeling that we're all probably familiar with is how you feel when you jump into a pool on a cool day. Even though if you took a thermometer and measured the water temperature, it might not be that much different than the air temperature, our skin feels much cooler in the water. This is because water and liquids in general are much better conduits of heat compared to air and other gases. Although it sounds kind of crazy, data centers are now immersing high-powered computing equipment in non-electrically conductive liquids to take advantage of this effect. Another option is to take the approach that our bodies take to dealing with extreme heat and exertion. Our first defense is to sweat or perspire. The thin film of liquid on our skin can then evaporate, which is an endothermic phase change process. Endothermic means it requires a heat input, which thankfully is provided by our bodies. Phase changes can be even more effective mode than forced convection. The most common industrial application I see is the common vapor compression refrigerant cycle used in heat pumps and refrigerators for over 40 years. Other newer applications include heat pipes used to cool electronics. One last option is to take a passive approach. Like this cyclist after a hot ride, if you want, you can put your body which you wish to cool in contact with a large thermal mass at a cool temperature with a highly conductive material such as steel or concrete. If you have a small or cyclic heat load, such passive heat sinks can be very successful. As shown on the left, we have one for a PCR cooling system for laboratory purposes. And to wrap up, we would be remiss if we failed to mention the critical role of engineering simulation in designing and validating potential cooling designs. We urge everyone to join the digital engineering revolution so that you don't have to learn the hard way through physical experimentation. CFD simulation technology is now broadly accepted, and our services make it highly accessible. Comment chill out if you'd like to hear about the many success stories we've been a part of in cooling applications.